The planet Jupiter is not what you might think. Most people misunderstand Jupiter because much of what we were taught about this planet in school is inaccurate. This is not simply a massive ball of gas. Jupiter is a liquid planet, and even more surprisingly, it is actually a planet made of liquid metal. Beneath those familiar clouds lies one of the greatest mysteries in our solar system. So let's take a closer look. This is the first close-up image of Jupiter ever captured. It was taken by a NASA spacecraft known as Pioneer 11 in 1974. And this is the first moving view of Jupiter, a time-lapse created from images captured by Voyager 1 as it approached the planet in 1979. The issue with these observations is that while they look impressive, they don't reveal much about the true nature of this gas giant. Instead, they raise more questions, such as what Jupiter is actually made of and how it became so massive. The true scale of Jupiter is extremely difficult to grasp. Not only is it enormous, but its mass exceeds the combined weight of every other planet in the solar system. It is large enough to fit about 1,000 Earths inside it. To give a clearer comparison, if Earth were the size of a grape, then Jupiter would be about the size of a basketball. Our standard theory of how the solar system formed begins with a vast disk of rock, metal, gas, and dust orbiting the newly formed sundae. Over millions of years, the material in this disk collided and gradually formed larger and larger bodies. As these bodies grew, gravity became stronger, pulling in even more material. According to this idea, Jupiter formed when one of these growing masses became so large that its gravity began capturing huge amounts of gas from the surrounding disk, continuing this process for billions of years until it became what we see today. This explanation is logical, and if it were correct, it would suggest that deep inside Jupiter there is a massive and extremely dense core made of solid rock and metal. Another theory, just for consideration, suggests that Jupiter may have begun as a separate, enormous cloud of gas located just outside the early solar system. Over time, this cloud grew so large that it eventually collapsed under its own gravity, forming a dense sphere of gas. This is essentially the same process by which stars form, except stars require a much larger cloud of gas. In this scenario, the result would be a very large planet, which was later drawn in by the sun's gravity and settled into orbit. If this were the case, Jupiter would not have a solid core at all. Instead, it would resemble a layered structure of gas. However, the theory most commonly taught is the one involving a large solid core that captured surrounding gas. While this idea seems reasonable and is not unrealistic, it is also not correct. Our first major breakthrough in understanding Jupiter came in the mid-1990s, and this is one of those rare coincidences that almost seems too perfect to be real. In July 1995, Jupiter was struck by a comet. Events like this are extremely rare, estimated to occur only once every 6,000 years. But in this case, we were able to witness it, and we had the technology to observe it in detail. The comet, named Shoemaker-Levy 9, was a massive chunk of ice and rock traveling through the solar system at a speed of 216,000 kilometers per hour. It is difficult to determine the comet's exact size because by the time it was discovered, Jupiter's powerful gravity had already broken it into several dozen fragments. Even so, the largest piece was still about 2 kilometers wide. At that time, NASA's newly operational Hubble Space Telescope was ready to observe the impact. However, there was a major challenge. The fragments were expected to collide with the far side of Jupiter, hidden from Earth's view. It seemed like we would miss the event, but at the exact same time this rare, once in 6000, year event was occurring, NASA also had a spacecraft arriving at Jupiter. This spacecraft was Galileo, named after the first astronomer to study the planet with a telescope. It had been launched in 1989 on a mission to explore Jupiter and its moons. It was scheduled to arrive in December 1995, and as it approached, it had a clear view of the comet impact. What it observed were 21 separate collisions over a period of 6 days, with the largest fragment releasing energy equivalent to 300 million atomic bombs, making it the most powerful explosion ever recorded on camera. As Jupiter rotated, the Hubble Space Telescope was able to observe the aftermath of these impacts. They left behind massive dark marks in clouds and produced enormous plumes of debris that rose thousands of kilometers high and remained above Jupiter for months. And this is what the Galileo spacecraft encountered. The inner material of Jupiter had been ejected into space, allowing the probe to pass directly through it. This gave us our first glimpse beneath the cloud layer that had fascinated observers for centuries. One of the most significant discoveries Galileo made was the presence of water, and a large amount of it. Scientists found this unexpected, unusual, enough to motivate the development of a new mission to Jupiter designed specifically to uncover the planet's true nature. That mission was called Juno. The spacecraft launched in 2011 and arrived in 2016 to begin investigating the mystery within Jupiter's core. So when we say that much of what you learn in school is incorrect, it's because we only began uncovering the real details within the past decade. Here's what wasn't known at the time. Jupiter is not made of gas. It is covered by thick clouds of gas that form its recognizable bands and storms. But these clouds are only a thin outer layer, above far more unusual conditions below. Let's start from the top. In Jupiter's cloud layer, temperatures drop below minus 100 degrees Celsius. Water ice crystals interact with ammonia, which acts as a natural antifreeze, allowing liquid water to exist in the upper atmosphere. As droplets collide with ice crystals, the clouds become electrically charged, triggering massive lightning storms across the planet. This extremely cold mixture of water and ammonia gradually forms slushy hailstones that fall into the lower atmosphere, where they melt into rain, evaporate, and rise again, continuing the cycle. These rising jets of hot gas that fuel the intense storms on the surface extend deep into the planet's atmosphere. This is what we observe in the Great Red Spot. Not only is it thousands of kilometers wide, but it also reaches hundreds of kilometers down into the ammonia rain layer. The red spot rises higher than any other clouds on Jupiter, extending above the surrounding layers and absorbing more ultraviolet light from the sun. This light reacts with chemical compound in the storm, producing its deep red color. Imagine a cloud 10 times taller than Mount Everest and 10 times deeper than the ocean, and even that comparison still falls short of the true scale of the red spot. As impressive as this outer layer appears, the average depth of these ammonia and water clouds is only about 50 kilometers. As we move below the clouds into Jupiter's lower atmosphere, the temperature begins to rise. This heat is caused by pressure. When molecules are compressed, their energy increases, and this pressure is generated by gravity. The immense mass of Jupiter pulls all of this material inward, compressing it more and more until unusual effects begin to occur. The deeper we go into Jupiter's gravity, well, the greater the heat and pressure become. It's similar to moving through a fog that becomes increasingly dense until it eventually turns into a liquid. However, in this case, the fog is not water, it is hydrogen. Hydrogen is the lightest element in the universe, and in extreme gravity conditions inside Jupiter, it is the only element that can remain In the upper layers, heavier elements have already been drawn down toward the planet's core. At a depth of roughly 1,000 kilometers below the cloud layer, hydrogen gas completes its transition into a liquid state. This is the closest thing to a surface on Jupiter, an ocean of liquid hydrogen, the largest ocean in the solar system. So while Jupiter may be covered by a thin layer of gas, it is certainly not a gas planet in the way it is often described. It is a liquid planet. But this liquid is far more unusual than anything we experience on Earth. On our planet, hydrogen can be turned into a liquid only by cooling it to extremely low temperatures. The atmospheric pressure on Earth lowers the boiling point of hydrogen to around minus 250 degrees. But on Jupiter, the opposite effect occurs. The extreme pressure raises the boiling point so much that hydrogen can exist as a liquid, even at temperatures exceeding 1,000 degrees. This ocean is roughly 20,000 kilometers deep, about 2,000 times deeper than Earth's oceans. And as we approach the bottom, the pressure and heat produced by the planet's gravity create a very unusual effect. Under pressures millions of times greater than those on Earth's surface, and at temperatures near 10,000 degrees Celsius, hydrogen changes into a state known as metallic hydrogen. This does not mean it becomes solid like steel. It remains a liquid. The metallic one, similar in some ways to the mercury found inside a thermometer. The most important change here is that metallic hydrogen can conduct electricity. Jupiter's gravity compresses the material so intensely that electrons are freed from hydrogen atoms and move throughout the liquid, producing an electric current. This layer of liquid metallic hydrogen forms most of Jupiter's interior. It extends to a depth of about 40,000 kilometers, and beneath all of this lies Jupiter's core, at least in a sense. Previously, scientists believed there was a compact, dense core at the planet's center, roughly the size of Earth and composed mainly of rock and iron. While this idea seemed reasonable, new research suggests something different. The core appears to be much more fuzzy, meaning the transition between liquid metal and solid material is not clearly defined. Instead of a sharp boundary, the layers blend together. This fuzzy core extends across about half of Jupiter's radius. Scientists now think it resembles a dense mixture of liquid, rock, and metal all combined together without a clear separation between different states of matter. At present, it is unclear whether this feature is unique to Jupiter or common among gas giants. Saturn has not been studied in as much detail, so we do not yet know if it has a similar internal structure. It is possible that this is completely normal. If Jupiter's core is indeed unusual, it may be the result of a massive collision early in the solar system's history. There could have been a rocky planet up to 10 times the size of Earth that eventually collided with Jupiter. The energy from such an impact could have disrupted and spread out the original solid core. This idea might also help explain how Jupiter became so large. While the collision theory is plausible, it is not yet confirmed. Recently, astronomers attempted to recreate the scenario using computer simulations. They tested many different cases involving planets of varying sizes and compositions colliding with a young Jupiter. Initially, the simulations produced the expected result of fuzzy core. However, in every case, the core eventually settled and formed a more defined, solid structure at the center of the planet. So, although we know Jupiter has this unusual core, we still do not understand how it formed. Despite everything we have learned, we still lack a clear explanation for how a planet like Jupiter comes into existence. And that is what makes Jupiter so interesting. It remains unusual, a vast mystery in the sky, waiting to be understood. And in time, we will likely find the answer